Okay, zero and negative indices. Now, the only difference about, the only main difference between a zero and a negative indice is the fact that, zero always gives a single value out all the time, and negative indices change the form of which our expression will look. So what we're going to do is we're going to say, we're going to define a few rules, and then we will apply them in some examples. So a to the power of 0, well, anything to the power of 0 is just equal to 1, okay? And it's a rule we're going to use. So, we're multiplying everything by themselves when we had any index that was 1 or greater. Okay, when we had 0, we're just going to make it equal to 1. And there's a cool little proof behind that one, and we might do that just to have a look at. So let's say that we have a to the power of m divided by a to the power of m, okay? So that is, we have a times a times a times a, m times, and a times a times a, m times as well. Okay. So let's say we have an m times, so a number of times, it's the same on the top and the bottom. So what happens is we can cancel the top and the bottom out, and we keep doing that, and it turns out all the top cancels with the bottom, so we're just left with 1, okay? So that's pretty much the rule for why a to the power of 0, or any number to the power of 0 is equal to 1. Okay, now with negative indices, it's a little bit different. So if we have a to the negative 1, then that is just the same as 1 over a. Okay, a to the power of negative 2 is just 1 over a squared, and so on. The pattern keeps continuing like that. Okay, so whenever we have a negative, in general, a to the negative n is just 1 over a to the positive n. Okay, so we're effectively saying anytime you have a negative index, okay, we can just rewrite the expression as 1 over the same base, but with the positive index. Okay, so let's have a look at some of these examples used in action. Now, in these ones, we have some negative indices, but we just apply them the same way as we do with the others. So 5 to the power, a to the power of 5, times a to the power of negative 12. Well, that's just equal to a to the power of 5 plus negative 12, okay? And if I actually drew my plus properly, that would have been much better. Okay, because remember, when we multiply indices with the same base, we just add the powers. So this is the same as a to the power of negative 7, which is the same as 1 over a to the power of 7. Okay. Okay. Now with b, okay. So b, we've got 3n to the negative 2. Well, that's the same as 1 over 3n to the 2. And we know that the power of power is going to change this to be 1 over 3 to the 2n, because we just multiply those powers together, which is the same as, oh no, we'll just leave it at that actually. So 1 over 3 to 2 to the n, okay? Let's have a look at a few more examples involving some other negatives. Okay, so we've got 5 to the negative 3. So what we're going to do is going to rewrite without the negative. So if we've got the negative on the bottom, okay, so this is the same as saying 5 divided by r to the negative 3, which is the same as 5 divided by 1 over r to the 3, positive 3. Now remember, whenever we want to divide some fractions, we can just multiply by the reciprocal of that fraction on the second side, which is then just the same as 5 to the r cubed. So the shortcut is that we just, whenever we have a negative, okay, you just swap the position it's on. So if it's on the bottom of a fraction, you put it on the top. If it's on the top of the fraction, you do the bottom. So let's apply that to this one. So we've got d squared over x to the negative 5. Okay, this is just the same as d squared x to the power of 5. Okay, so just putting it on the top of the fraction with the negative, with the positive value of that. So that's negative and positive indices. Not a very long video, but a very important one because they do pop up occasionally, particularly when we look at exponential graphs.